11.4, the cross product. So we worked with one type of product for vectors last time. We worked with the dot product. And when we take a dot product of two vectors, what do we end up with as an answer?
Just a single number.
Just a single number. We sometimes call it a scalar. We end up with a scalar or a number as our answer. So what we're going to take a look at with cross products is something a little differently. So we have many applications in physics, engineering, and geometry that involve finding a vector in space that is orthogonal to two vectors. What did we say orthogonal meant last time? Perpendicular, yeah. So let's picture our classroom, since we can do a 3D space and have some sort of an image like that. So imagine the two vectors you had are along the ceiling, the wall behind me and the wall to the side of me. So there's a vector coming sort of out of the corner this direction behind me, and there's a vector coming out of the wall, and it's perpendicular to that one. Now, I didn't necessarily have to create perpendicular vectors to do this, but they're perpendicular anyway. It's nice enough to work with. If you want to create the perpendicular vector to those two vectors at the same time, it would be the one coming down the wall toward the floor, right? So there's a unique vector that will do that, and the cross product will find that unique vector. Okay, so we're finding a vector that is perpendicular to two vectors when we find the cross product. Now, in order to do that, I had promised you we were going to look at some linear algebra, some matrices, and we are. Specifically, we're going to look at the determinants of matrices today, okay? So a refresher or a first time if you haven't seen this before, the determinant of a 2 by 2 matrix looks like the matrice notation, except that it has sort of looks like absolute value signs on the either side, right? They're not, they're not like this. It's not a matrice where it looks like that. So these bars on either side mean to find the determinant. So I'm a really visual person, so you're going to see me drawing these out all day, even though you may not need to, and if you don't need to draw them as we continue, that's okay. But what a determinant does is you multiply along the first diagonal, top to bottom, so top left to bottom right, and then you subtract the multiplication, so I'll draw an arrow. You subtract the multiplication when you multiply up the other diagonal. And that gives you a scalar. Right, you get a number when you're done with this. So we have A1 times B2 minus A2 times B1. So if you want to memorize it from the perspective of, a formula perspective, there is one formula there. It's right there. I'm always going to think about it visually. That's what my brain does. Okay, so you're going to see me drawing a lot of these. Now, for a 2 by 2 matrix, you can probably eyeball it and just do it, and that's fine. We'll do some in a minute. For a 3 by 3 matrix, it actually creates a third sort of caveat to what's going on. So what happens when you have a 3 by 3 matrix is that it's a combination of 3 2 by 2 determinants. So when you're trying to find a determinant. So what you do is you take, and you can actually do any row and any column. We're specifically going to choose the top row because it lends itself well to vectors. But as a general statement in linear algebra, what we're doing is something called expansion along minors. So you pick a row or you pick a column. We're picking our top row. And you see those as the coefficients in front of each of these, right? There's the coefficients in front of each of the determinants. So that's where the first row goes. And then what you do is whichever entry you are in on the row, so let's say you're right here, you sort of ignore the row and the column that it's on, and you get the determinant in the other quadrant, the other corner of the picture. So we see A1 in the top left-hand corner, and we see all the pieces in the bottom right-hand corner in the determinant notation inside here. Okay, so then we move on to A2. So if we're doing A2, we zero out the row and the column it's on, and it leaves us 4 other pieces. Those are the 4 pieces that go in the determinant next to it. So we have B1 and B3, C1 and C3. Then, oops, that was supposed to be cut. Let's try again. We do the third coordinate, A3, and we do it with this bottom right-hand corner, or left-hand corner, over here. So again, we zero out this row and this column, and we have B1, B2, C1, C2. Do I have all those details written in correctly? I'm not looking at my whole screen. You are. Does that look okay?
Is there supposed to be a plus sign on that last
on the A3?
Yeah.
There is. So I haven't mentioned that yet, but thank you for mentioning that because that's what I should mention next. Do notice that the signs are different. So when we are doing this, the first one is positive, the second one is subtraction, and the third one is addition again. So that is what we want to see happen. That is correct. We will alternate the signs, positive, negative, positive. Now, I would be remiss if I said that this is just how you have to do a determinant. You can do it along any row and any column. So we could expand along minors along this row, if this row, or this column rather, this column if you wanted to. And you could put A2, B2, and C2 in those front locations. And you could zero out the row in the column, and you could use the other ones. For example, if you were using B2, you'd zero these pieces out, and the determinant would be created from these 4 pieces. Okay, so you can do it with any row, any column. But what we're doing in the class for what we need right now is we need it to be the top row. So ours is always going to be the top row, right? So that's why it's written this way on this screen. So what's the connection? Well, we can actually find the cross product by using these determinants. So along the top, the row, the first top row, is our component vectors, I, J, K. The second row is the first vector in our cross product. And the third row is our second vector in our cross product. So it's always going to have I, J, K along the top, and then we're going to have U in the middle on this one, and then V on the bottom because it's U cross V. Okay? And then it works the same way. So you see the coefficients, if you will, of each of our determinants are the I, J, K. And then the components inside of the determinant come from the other corner. So the I is U2, U3, V2, V3. When you do J, you do U1, V1, and U3, V3. And when you do K, you do U1, U2, V1, V2. So what I was referencing before is you're going to see me write this out every single time. If you can eyeball it and not write it out, that's okay. There's nothing wrong with that. In fact, the notes that I was looking at from last year when I did it, I didn't have the IJK, I didn't have this actual determinant written out every time. I know I did it because that's how I think about it, but I didn't have it written out. When I did it this time, I wrote them all out every single time because that's how my brain thinks about these, is in a very visual way, okay?
So you don't have to write that piece down?
You do not have to, but you'll still write the piece after it out every time.
Oh, you just, okay.
The right-hand piece you'll need. But if you can go from just knowing what U and V are, right, because we're going to have numbers in here, and knowing that the IJK is along the top, you can jump to that point at the end if you wish without this in-between step. So this piece right here is the optional piece. Okay? So write it or don't write it depending on your need for it. So we got to do some examples. I mean, we're going to do lots of examples. There's some other things cross product tells us. We'll see a couple theorems here in a minute. But right now, we're just working on like the computational component of how to do the determinant. Okay? So we're finding 3 different things: U cross V, V cross U, and V cross V. And our vectors are U is equal to 2, negative 2, 0, and V is equal to 3, 0, 1. Okay? So our first one, part A, U cross V. So if I'm doing U cross V, I'm going to write out a vector. I'll actually write it above. In this space above, we've got some space. So I'm going to have the IJK. And then I'm going to have U in the middle. So U is 2, negative 2, 0. And I'm going to have V at the bottom, 3, 0, 1. So for U cross V, it will start out with having the I, right? We're going along the top row. And the IJK is always in the same order, so that's going to be a given. I want the determinant that's not in row I. So I'm looking down here, because these are the rows and columns that don't involve I. So I need to have negative 2, 0, 0, 1. So I have negative 2, 0, 0, 1. And then we have minus, remember the middle one is always subtraction, the vector J. And I need the determinant that's not in row J. So that's going to be the two pieces on the outsides. So it's going to be 2, 0 along the top row, 3, 1 along the bottom row. So I have 2, 0, 3, 1. And then the third one is K. And for K, I want to have the component that's not in the row or column that K's in. So I'm going to have 2, negative 2, and 3, 0. Okay, so you're going to write that down. And then after that, you're going to do some multiplication. So the first piece is going to have an I. For this first one, I'm actually going to write down a little bit more, and then I'll stop writing quite as much after this. But we want to have the diagonals, right? So we're going to multiply down and then multiply up. So I have negative 2 times 1, that's negative 2. And then I have minus, and then I have the 0 times 0, which is 0. Then I'm going to have minus j. I'm going to multiply the 2 times 1 and then 3 times 0. So I have 2 times 1 is 2, minus 3 times 0 is 0. Plus k. Same thing, we multiply down and then we multiply up. So 2 times 0 would be 0, minus 3 times negative 2, which should be plus 6 here, yeah. So I have a plus 6 minus a negative 6, okay.
Do we need that step?
You mean write down minus negative 6? This step that I just wrote?
Yes.
No. This is the only time I'm going to write it.
Okay.
I'm going to jump to the end of the next one. I just wanted to write it one time.
Okay.
Yes, you do not have to have this step. And then you're going to simplify. So you've got negative 2 minus 0, so that's negative 2i. We have, let's see, 2 times j, so negative 2j, because the j is negative. And then we have 6k. And if you prefer, you can write that component-wise. This is negative 2, negative 2, and then 6. Okay, so part of why we're doing part B is to examine whether this is commutative. We've had a lot of things that have been commutative. Commutative is a common feature. We're going to do V cross U. So if I'm doing V cross U, it means that my second row and my third row up here are switched. All right, so U is on the bottom now, and then V is on the top, or in the middle, I should say, and that's 3, 0, 1. Okay, so I'm switching the two rows, and what we're basically seeing is whether or not it yields the same vector. Okay, so we're doing U cross V. So again, I'm going to write out this step. This is the step that's optional too if you wish. You don't have to write this out. But if I use these corners, so this is the last time I'll actually mark them out too as a reference so that we can see it. But I've got 0, 1, negative 2, 0. Minus j. So with j, I need the outer pieces. So I have 3, and then 1, and then 2, and then 0. And then I have plus k. And k would be this corner over here on the left. So I have 3, 0, 2, negative 2. Okay, so I'm going to short us one step from last time. If you want to write it out, feel free to do so. But we're multiplying down. I have 0 times 0 minus negative 2 times 1. So what do I get if I multiply those out? 0 times 0 minus negative 2 times 1.
Like the end or just
2. Yeah, the end result, this will be 2. So if I multiply down, and then I add what I get to it, subtract what I get to it by multiplying up, I'll end up with a 2. If you need to see more work, definitely show more work. The next one, oops, let me put that there a second. So I have 3 times 0 minus 2 times 1. What does that give me?
plus 2j.
Yeah, so it would be a negative 2, and then the j itself is negative, so I get plus 2j. And then the third one, I have 3 times negative 2 minus 2 times 0.
Negative 6k.
negative 6k. And if we write these out, we see that we got a 2, 2, and negative 6. Did we get the same vector?
No, but we did get the same.
Well, yeah, but this multiplied by -1 is a scalar.
Okay, so we didn't get the exact same expression at the end. It's multiplied by -1 at that, like we compare them. So they're scalar multiples of each other, right? Which makes the vectors what?
Parallel.
Parallel. Does it make sense that you could have a parallel vector? Sure. Yeah. And so, in some sense, what's happening here, like my side of my wall, right? I was talking about the vector that came down, right? My wall. What do you suppose is happening if I created that other vector? It went up. Sort of, it's the other half of the line. If you could think about vectors as creating a line, if you were to put them end to end, right, like that. So it is a parallel vector to what I have. It's a vector in the opposite direction, but it's the same vector. Okay. All right, one more. We're going to do V cross V.
We lost you.
Wonderful. All right. So the third one here is to do V cross V. So that would actually create this vector, right? Or this matrix at the top. So I have the IJK and then I have 3, 0, 1, 3, 0, 1. All right, so we're going to expand along minors. So we have our I. And then what numbers are going to go into the matrix next to it?
0, 1, and then 0, 1.
Yep, 0, 1, 0, 1. Minus J. What would go in the matrix next to it?
3, 1, 3, 1.
Uh-huh. And how about after K?
3, 0, 3, 0.
Okay. All good? So what happens when I do the multiplication for the determinant of the first matrix?
0.
You get 0. So it's 0i. What happens when you do the multiplication in the middle?
0.
So I have minus 0j. And when you do the multiplication on the last one,
0.
you get minus or plus 0k. This created the 0 vector. Okay,
Will it always do that if you multiply it by itself?
it's a very good question.
So I know there's the zeros in the thing. Oh, okay.
There you go. That's the answer for you, Adeline. Yes, it will. So this, I mean, we're not proving them in the sense that they're arbitrary, but we did a couple of examples of some of these, right? So we did an example of the first one. So U cross V is the opposite of V cross U. And we did an example of number 5, which is U cross U is 0. So when you do the cross product with itself, or do the cross product of a vector with itself, or if you do the cross product in a different order, these are the two of them. There's some others here as well. So you see number 2, a distributive property. On number 3, you see an associative property that looks a lot like the associative property we had for dot products, actually. On number 4, you have the multiplicative identity for cross products, where you get 0 back. And then, or the 0 property, not multiplicative identity, the 0 property is what I meant to say. And then on number 6, you actually see an interaction between the dot product and the cross product, which might feel even a little bit counterintuitive.
On the homework, is there, like, say we have like a part A and a part B that says, like we had on this one, we had
Yeah.
V times V and V times C. Could you just say,
Like cite the property or
cite the
something for
property
it.
and just say
Mhm.
it's a negative, so you
Yeah.
have to work out on it?
You wouldn't have to, yeah.
Okay,
So we did it by hand to try to get us to this point of recognizing that seems reasonable.
okay,
Yeah.
cool. I'm assuming we can do that with all of them.
Mm-hmm. Yeah. You might find it more difficult to actually look for all the properties if they're not something that's super obvious, but if you noticed one, then it's probably easy enough to use. So,
Yeah, like the 0, 1.
yeah,
Just
yeah,
like-
exactly. If you're multiplying by 0, you get the 0 vector, right? That's nice. Okay, so these are algebraic properties of the cross product. This is theorem 11.7, and theorem 11.8 is actually the geometric properties of the cross product. So we've got more properties after this one.
May take a picture if you want to go to the next slide.
Okay, that'll work.
Yeah,
Go for it.
yeah. So,
You good? Okay, all right. So the geometric properties, there's only 4 of them as opposed to being 6 of the other ones. Describe some of the things we already said. For example, number 1, U cross V is orthogonal to U and V. That's what we've created. We've created an orthogonal vector. We're going to actually test and prove, well, not prove, but proof by example, if you will. Like we're going to show an example of that actually happening in a minute. The second one gives us a trig relationship between them. So the magnitude of U cross V is the magnitude of U times the magnitude of V sine theta. U cross V is equal to 0 if and only if U and V are scalar multiples, i.e. parallel. So number 5 on the algebraic properties above would be a very special case of that, right? But it would be a case of that, right? U is parallel to itself kind of thing. You know, has the same direction and magnitude. So it's parallel to itself. And number 4 might be the most interesting one, is that not only does the U cross V vector create an orthogonal vector, but the magnitude of it is the area of a parallelogram. So I kind of feel like this is similar to what happens in Calc 1 when somebody uses lots of verbiage for the same stuff. So in particular, we talk about it with derivatives. So there's a list that I usually make, and it's got derivative on the list, but it also says things like slope of the tangent line, limit of the slopes of the secant lines, slope of the curve at a point. All of those mean the same thing, which means the directions will sometimes vary, but they're actually asking you for the exact same quantity, right? So be prepared for that, or at least a similar quantity. They're using, in this case, the cross product to find a variety of different things. Okay, so depending on when you printed out your notes, number 2 may not have the vectors on there. I realized it this morning as I was filling it in.
That's why I was confused.
Yep.
It's like, if we
So
just-
fill those in. I fixed it this morning. So if you've printed out your stuff since about 9:30, it's on there. If you printed it out before about 9:30, give or take, it's missing. But those are the U and the V that got left off of my original notes. Yeah, if you didn't print it off at all, you don't have to worry about it at all, do you?
How come time constraints be like that?
All right. Did you get your picture, Zach?
Yep.
Are you good?
Yep.
From the previous slide? Okay, good. Okay, so we have a U and a V. So that's actually should say A at the beginning. Find U cross V, and B find V cross and V cross U, and then show that it's orthogonal to. And this is not worded very well. So it's orthogonal to U and to V. Yeah, that's fine. It's okay. Orthogonal to U, which is -1, 1, 2, and orthogonal to V, which is 0, 1, 0. I'll reword that and it'll sound better later. But we're going to find 2 things. We're going to find V cross U and U cross V. And we're going to show that what we have found is actually orthogonal to what we would originally have had with U and the V. So there's the B is supposed to be here, and B. That's where the B is supposed to be. Okay. So A is to find U cross V. And as promised, I'm going to write them out each time. So we have IJK. And U is -1, 1, 2. V is 0, 1, 0. All right, so we have our I. 1, 2, 1, 0. J. negative 1, 0, 2, 0, plus k, negative 1, 1, 0, 1. Okay, so far so good. Okay. All right, so what is the first determinant value? Negative 2, and then it's got our I component. Sorry, there's a typo here. That should have said minus j. My apologies. Minus j. Make sure yours says minus j. All right, so what's the second determinant value?
0j.
Yeah, it's 0, so feel free to write plus or minus 0. It doesn't matter, and then j. And then how about my last one?
Minus 1k.
Right. Yeah, I'll put minus 1k because we can actually turn them into the component form if we want to, a little bit nicer, but feel free to write it or not write it. So my vector is negative 2, 0, negative 1. Okay. If I were to do, I'm not actually going to do it because we don't need to, as we pointed out, v cross u, what is v cross u?
Negative 1 times.
Yeah, just the opposite sign of all of ours. So what would it actually read?
2, 0, 1.
2, 0, 1. Right. So part B is actually showing that these are orthogonal. So take a look back at what we said about orthogonal. Well, it wasn't in this lesson. It would have to be in your last lesson. What did we say happened to the dot product when things were orthogonal? The dot product is 0. Okay? So if we have orthogonal vectors, which we should have them now, the u cross v is supposed to be orthogonal to both u and v. If we've got the correct thing, then we should be able to get a dot product with u and v individually that's 0. So we're going to do u dot u cross v. Okay, so u is listed above. It's the negative 1, 1, 2. And then the u cross v is the one we just found. So I'm going to write it out just because we've got lots of pieces here. So if you look back later, you're like, where did all these numbers come from? So the u value is negative 1. The u cross v value, we're going to use the first one, it's negative 2. And then our j component is 1, and our j component of u cross v was 0. And then our k component is 2, and the cross, or the u cross v component was negative 1. So if I do negative 1 times negative 2 plus 1 times 0 plus 2 times negative 1, what will I get? 0. Now, let's think about what happens if I switch it. If I do times v cross u, will I also get that? So let's just confirm. All that changes is the signs on the numbers in parentheses. This should now say 2. The 0 is, of course, going to say 0. And this should now say 1. Do I still get 0? Yeah, I do. Now, it's not quite everything I was asked to do, but we're getting close. Running out of space, though. So we have found that u dotted with either u cross v or v cross u is 0, so it verifies that it is going to be an orthogonal vector to u. We need to do the same thing with v. So we're going to do v dotted with u cross v. So v had the components 0, 1, 0. So it's 0 times negative 2 plus 1 times 0 plus 0 times negative 1.
That's 0.
That one's 0. In fact, each component is 0. Right? Each of the three things added on this one is 0. So I kind of like this one because you can see that this one's zeroed out completely. Like each piece was 0. But the first one didn't do that, right? They just summed to 0 when they were done. So it can happen either way. And just so that we can say that we've done it, check the other part too, we'll do v cross u. But switching signs won't change anything because I'm multiplying by zeros everywhere along the way. So 0 times 2 plus 1 times 0 plus 0 times 1, also going to be 0. So we've verified for this specific example that in fact the cross product is orthogonal to each of the original vectors, which was a statement that we had said before too. So we're not really proving things in general, but we are definitely seeing verification of what we're doing so that it seems like it's a reasonable statement. All right, we've looked at unit vector stuff before, so we're going to do a unit vector problem next, number 3. Number 3 wants us to find a unit vector that's orthogonal to u and v. So think about what we would have to do to do that. How would we find a unit vector that is orthogonal to u and v?
Would we use one of the geometric properties at all?
We won't need to.
Are we setting something equal to 0?
Nope.
Do you find the cross vector and then find the unit vector of the cross vector?
Yes. Okay, so do we know how to find the cross product? Sure. What does the cross product find for us? In this
Something
description.
perpendicular.
Yeah, it finds an orthogonal vector, right? So if we find the cross product, we will have a perpendicular or an orthogonal vector, correct? But we want it to be a unit vector. So how do I create a unit vector out of a vector?
Vector over magnitude.
Yeah, we divide it by its length, right? So in order to create something that's a unit long, you just need to divide it by its length, which in our case, we're looking at magnitude. Exactly. So once again, I'm going to create the IJK matrix up here. So the unit vector, or not the unit vector, the u vector is 3i, negative 1j, and then there's no k, so that's a 0. And then for v, I have 0 i's, I have 4 j's, and I have 1k. This is my matrix. And we will find u cross v for starters. So u cross v, we have I, and we need the bottom right-hand corner, so negative 1, 0, 4, 1, minus j. We have the outside pieces, so I have 3, 0, 0, 1, plus k, and k is the bottom left-hand corner, which is 3, negative 1, 0, 4. Okay, first determinant. What's the value?
-1.
So negative 1, so now I have negative 1i. How about my second one?
Uh, 3?
Mm-hmm.
Negative 3.
Yeah, it's 3, and then we have the negative j, so negative 3j. What is the determinant after the k value going to be?
12.
Yep, so we have a 12k. Okay, so this is an orthogonal vector. Notice I said an orthogonal vector. It's somewhat unique, I mean, right? Like it's not just random, but it can be created in a unit form, so there's not exactly unique. So how do I find the unit form of it? I need to find the magnitude. So I want the magnitude of u cross v. So all of everything I just wrote above, how do we find magnitude? Remember?
Square root of all the things squared and added.
Right, square root of the sum of each of them squared together. So I have negative 1, so I'm going to ignore my negatives because they're going to all square. So I have 1 squared, 3 squared, and 12 squared. Since I'm squaring, I can ignore the negatives. So do some real quick math, add that up. 154. Check to see, does 154 rationalize? Anything come out of it? No.
11 and 2.
No.
7, 11, and 2, so there's no duplicates, so square root 154 is the simplest form. I think it is, isn't it? 7, 11, and 2? I think I did it earlier today. Yeah, 7, 11, 2. Okay, so what would I do to find my unit vector now that I know these two pieces?
Take each piece and put it over the magnitude, so
Right.
negative 1 over 1.
Yep. So in general, just so that you have it written down, perhaps, you're taking the u cross v that we got above, and you're dividing it by the magnitude of u cross v, right? That's how a unit, make things into a unit vector anytime, whatever it is, it's divided by something's with its magnitude. So we have, and again, I'll write it for the sake of writing it down one time, we have negative 1, 3, negative 3, and 12. And it's divided by the square root of 154. That's in general what we're going to do. But we're going to do it like you just said, Zach. We're going to write each of them that way. So, and I'm going to rationalize as I go. Is that all right? So I have negative square root 154 over 154. I have negative 3 square root 154 over 154. And I have 12 square root 154 over 154.
Last one can simplify.
It can, you're right. I think the others, in fact, the middle one can too, can it not?
No.
Oh, no, it doesn't. So it's 10, yeah, you're right, okay. So, but the last one can. So, yes, we'll have the square root, negative square root 154 over 154, and negative 3 square root 154 over 154. And then the 12 and the 154, they'll divide by 2, right? I think it's the only one. So I have 6 square root 154. I'm off my screen. Let me get some space just a second. So 6 square root 154 over what? 77. It's really sloppy there at the end, sorry. Screen is just not quite big enough on the iPad itself. Okay. Ready for our last example? Our clock is way wrong. I need to get some new batteries. We're going to find the area of the parallelogram that has vectors u is I plus j plus k, and v is j plus k as adjacent sides. What is it asking us to do?
Use theorem 11.4.
Theorem 11.8, number 4, which says I'm going to do what?
Take the magnitude of u cross v.
All right. So I need u cross v, and then I'm going to take its magnitude. So I'm kind of going to do the same thing I did in this last problem, but I'm not going to have to create the unit vector at the end, right? Yeah. All right, so again, I'm going to write my IJK matrix up here. So u is 1, 1, 1, and v is 0, 1, 1. That's a very nice, simple vector, zeros and ones everywhere. So we're going to have I, and then it will be the 4 ones, minus j, and it will be 1, 0, 1, 1, plus k, and it will be 1, 1, 0, 1. Is that all right for everyone? Okay, so the first vector, actually let me go back a step. I have determinant 1, 1, 1, 1. What's that give me? 0. So this is 0i. How about my second vector, or my second determinant? Yeah, it's a 1, so then I have a negative 1j. And how about my k component? Also 1, but it's positive this time, so 1k.
Is the middle negative or positive?
The middle is positive, but the j itself is a negative in the formula.
Oh, yeah.
Is that okay?
Yeah, I wrote it down.
Be sure it's not something wrong. No problem. And then we're just to find the magnitude of this. So magnitude means I'm going to have the square root, and then what am I going to do?
0 squared plus negative 1 squared plus 1 squared.
Yeah, it's technically negative 1 squared in the middle. I left mine off because I'm going to square it anyway. So what does this give me?
Equal to
Square root of 2. So the area of the parallelogram with adjacent sides u and v is the square root of 2.